Okay, section 22.5 plus part of 22.6, the direct alkylation. So 22.5 discusses acidity of a variety of these carboxylic acids, ketones, and aldehydes that all have this carbonyl functional group. This is table 22.1. You should take a look at it. I've reproduced it here. I've already drawn it. So let's take a look at it. First, our touchstone and acid. Acetic acid has a pKa of around 5. They've rounded off in this table. This is what I would encourage you to know. It's good to know a specific number for some representative of each group. You have to have a good sense of the relative acidity or basicity of compounds. So acetic acid is around 5. Now, if we have a diketone, the pKa is 9. Now, which protons in this compound? This is acetoacetone. Which protons? They're alpha protons here, but those are going to be like acetone, right? Remember that was 19. These are the acidic protons in dicarbonyls, the one that's alpha to both carbonyls. We've already looked at that a little bit in the introduction. Go back and review that if you need to. Now if we go from a ketone to one ester, we see that there's an increase in the pKa by 2 units, which means a decrease in the acidity. If we then switch the other ketone to an ester, another 2 pKa units. So again, these protons are less acidic by 4 orders of magnitude. So ketones are more acidic than esters, and we would expect that, right? Because the lone pairs on esters are pushing toward the carbonyl and making it less electron withdrawing. Thus, they're not as stabilizing of the anion. Now, remember our alcohol functionality. Methanol being our representative here is about 16. Acid halides, acyl halides that we saw in the HVZ reaction. Again, here are the acidic protons. You should be able to identify acidic protons in any compound. So 16. Then an aldehyde. You see, an aldehyde is more acidic than a ketone. And again, it's the protons here. It's more acidic by 2 pK units. Ketone is around 19. Then look, when we go from a ketone to an ester, we saw this impact in the dicarbonyl compounds, but we see it's even more dramatic here. This is 6 pK units. 10 to the 6th to go from a ketone to an ester when we replace that methyl group with a methoxy. And that's because the lone pair is pushing electron density and destabilizing the anion. Now, remember nitriles? We said they were like carboxylic acids. And here we see where that's true in the acidity. So a nitrile has about the same acidity as an ester. Now, then we go to the amide. Amide with the nitrogen. Nitrogen's better at donating those electrons, so it destabilizes the conjugate base, which would be the deprotonated alpha position even more. So that's a pKa of around 30. Now, the final one, we started with an acid, and then we're going to bracket it with a base. Why? Because the conjugate base of this acid, this is diisopropylamine, the pKa is 36. So what that means is if we deprotonate this, say with butyllithium, we make lithium diisopropylamide, or LDA, which is a strong base. And 10 to the 36th versus, say, 10 to the 17th, what do we have there? That's almost 20, it's 19 factors of 10, or 10 to the 19th. So what we will see is if we react a carbonyl group, say cyclohexanone with LDA, then we get quantitative conversion to the enolate plus the amine. And we can take the pKa's, 36, and the pKa of cyclohexanone is approximately 19. And so the equilibrium constant here would be, okay, is approximately 10 to the 17th. I didn't do that math right, did I? 10 to the, is that right? Yeah, the ketone is 19, 17. That'll be 36. So, for synthetic purposes, anything above 1,000 is effectively quantitative and irreversible. Okay? So this is a strong base. It's also a kinetic base, we'll see. That is, it takes the least substituted proton. All right, so that's LDA. Then what can we do with this? We can alkylate these. So let's look at the general reaction. If we take a carbonyl compound, and there's a whole variety of X's that we can use there. I'm going to illustrate a few of them. We can deprotonate those with LDA and then add an electrophile. Now this will be an SN2 reaction, and so it will have all the limitations of a normal SN2 reaction. We produce to it. So that's a general reaction to illustrate using LDA to kinetically and essentially irreversibly form the enolate. Then we can alkylate the enolate by direct alkylation at the alpha carbon. All right, so now let's look at some specific examples. If we take an ester, we can treat it with LDA, and we will follow that treatment with methyl iodide for illustrative purposes, and we put the methyl group here. If we use benzyl nitrile, again, remember, here are our acidic protons. Those same conditions. We can alkylate the position alpha to the nitrile. Now, we've talked about the carbonyls. There's the alpha position. Here's the nitrile. That's the equivalent of the carbonyl carbon. So this methyl group here is the corresponding alpha position for a nitrile. And then finally, to illustrate some kinetic basicity, we can differentiate these two different kinds of hydrogen. So there's a CH2 here and a CH group here. In LDA, we'll do it under kinetic conditions, 0.95 equivalents of LDA. Then we'll follow that with methyl iodide. And there are two potential products. We can alkylate the tertiary carbon, or we can alkylate the secondary carbon. And LDA is, as you might expect with these large diisopropyl groups, it's sterically congested. So we get 6% of the dimethyl, alpha-alpha dimethyl on the same carbon. And then the alpha-alpha prime product is present in 56%. So that's approximately a 1 to 9.3 ratio of those two products. Now, this is effectively the third reaction there in section 22.6. I've put that in so that we can see the acidity, we can do the deprotonation, and we can take advantage of that deprotonation to make carbon-carbon bonds. Are you classifying your reactions now? These are all carbon-carbon bond-forming reactions. And we want to keep that in mind because, again, when we are looking at a larger synthetic problem, if we identify that we need to make a carbon-carbon bond, that dramatically limits the number of reactions we need to worry about or that we need to remember.